just now. So please, the floor is yours, Peter.
Thank you very much, Norma, for that very generous introduction. I hope I can live up to it. The problem is that I have moved around quite a lot in my career, and therefore it makes it hard to give an introduction if you mention everywhere that I've been, because I've been in quite a few different places working over the years. I also a little bit nervous after Norma read out some of the names that are in the audience. Of course, I can't see all that from there, and so it's slightly intimidating to be talking to a screen, knowing that there are some very eminent figures in the audience. But I hope this goes down reasonably well. I apologize for the slightly pretentious title of this talk. The reason why I chose the title, well, of course, it's a bit of a pun on the State of the Union, but it just reminded me when I was given the task of writing, presenting a talk in this series, that about 15 or 16 years ago, I was asked to write a review article in Nature for the centenary of Einstein's Year of Miracles, because 1905, his famous papers that everyone knows now. And so I was asked to do a review on cosmology, and I called it The State of the Universe. And when I was asked to do this talk, I thought I would kind of resurrect that title and see how much has changed in the last 15 years. I mean, in cosmology, we talk a lot about how much progress there's been. And I think for at least 30 or 40 years, people have been saying that for the past 20 years, we have seen dramatic advances in cosmology, which is how I started this talk, this piece. And but it's interesting actually looking at that article that actually, although there's been fantastic progress and we've learned a lot of new things, it's been since 2005 a kind of it's been evolution rather than revolution, I think. I mean, we've understood more quantitative information, but the same big challenges are still there. And so what I wanted to do was to not by any means a systematic survey of cosmology, but just to pick on some aspects of it and some general kind of approaches and make some general comments on where we are in cosmology at the moment. So I'm going to move on. Of course, we now know this was kind of the picture that appeared in 2005 after, or around about then, with WMAP. It kind of established the standard model that we have now, plus or minus a few details. And this is what also NASA are very good at making public science graphic images that everyone can use. So here's an example of one of those. So we see the standard cosmology has all these buzzwords in it: dark energy, accelerated expansion, and inflation, and of course the cosmic microwave background. That was the picture that's established here. And the standard model of cosmology is pretty much the same now. It hasn't changed that much. That's the picture. One of the changes, of course, is that this is the angular power spectrum of fluctuations in the CMB, temperature fluctuations in the CMB from WMAP. And now we have from Planck, a much higher resolution map of the CMB, and different color scheme, of course, as well. That's one thing that does change with time, is that people's color palettes change. And then, of course, a much higher resolution power spectrum. You don't get much better information down at low multiplars, large angular scales, because basically we've only got one sky and can only, you know, a bit of cosmic variance problem there. But we have exquisite information at high frequencies. So the peak, people call the Doppler peak or the acoustic peak, is recovered, but Planck gives us some harmonics in the spectrum there, which are very probative about the parameters of cosmological models. So again, I'm going to show you things that I've collected over the years, and they're not necessarily the most up-to-date things, but they're all sort of qualitatively correct. You'll see that basically the Planck, the Planck and WMAP have consolidated cosmology into a 6-parameter model, which is a good fit to the CMB data, and it actually turns out to fit a lot of other things as well. The 6 parameters here are slightly strange ones. They're not the parameters that we would have used maybe 30 years ago, but we basically have the baryon density, the dark matter density, there's an acoustic scale, optical depth, and then 2 parameters that describe primordial density fluctuations. The thing to say is that our standard cosmological parameters that we learn now as or used to learn as undergraduates. I remember a paper that was one of the first that I read in cosmology when I was studying it, by Alan Sandage, and it was called Cosmology, the Search for 2 Numbers. And those 2 numbers were basically H0 and Q0, the deceleration parameter. Now we've advanced to 6 numbers, but H0 isn't one of them. Neither is Q0 for that matter, but it does to do with the deceleration parameter, or acceleration as we call it now. The Hubble parameter comes out around about 60 if you use the Planck figures. I'll come back to that shortly, because obviously the Hubble tension is a big thing. So in the modern era before Planck, we basically had so the 3 main components that we talk about are their dark energy. I'll say something about this later, of course. Dark matter and dark energy, and ordinary matter, baryons to you and me, have changed a little bit, but not kind of in any drastic way. So I've just been spending the last couple of weeks doing student examinations. And if these were exam results, we would say that actually dark energy was on for first class degree before Planck, but it's dipped into the 2-1 territory now. So it's not, there are some disappointments and changes, but basically it's pretty stable. The parameters change a little bit. I should say, of course, that it's not just the CMB that produces cosmological parameter constraints. It's a combination of things. But if you use a combination of things, you tend to get a multi-dimensional parameter space, and you don't get single constraints on one variable. You have to, on one parameter, you have to marginalize over them. So you'll see that the Hubble constant things, this is not using CMB, this is using baryon acoustic oscillations and some other things, and the Planck data shown here in the blue, that if you want a really low value of the Hubble constant, you really have to change omega, the matter density as well. So what I'm saying here is that one-off statements about individual parameter values are a little bit misleading, because there's a whole multi-dimensional parameter region that you have to take into account when you talk about individual ones, marginalizing over the others. Now, just in a historical frame of mind, I thought I would show you this. This was the state of the universe in the middle of the 1990s. This was at a summer school where it was very hot, actually, in Leiden, a graduate school, and there was a panel discussion. That's me in the middle, by the way, in case you hadn't realized it. I was a bit slimmer then. I didn't realize you could see I was wearing shorts either. The others are Alain Blanchard, John Peacock there, Bernard Jones, Vincent Icky, Rien van der Veegart, and Peter Cathcart. And in the panel discussion, we were asked to give what we thought were the right values for the Hubble, for the cosmological parameters, curvature, the age of the universe, and the density parameter. And you see, actually, quite uncannily, Rien van der Veegart was pretty much bang on the money for his choice, although we didn't have supernova acceleration in, I think this was 1994. I went for a low density open universe with no cosmological constant. He was the only one who wanted a lambda. And so he deserves the credit for this. But of course, science isn't decided by panels like this and votes and just kind of subjective preferences. It's determined by data. So I thought I'd just go on a little bit and say something about the Hubble constant. So I'm going to talk a little bit about anomalies and unknowns and things later on in this talk. But because there's quite a lot of interest these days, indeed a little bit of hysteria, in my opinion, about the Hubble tension, I thought I'd just do a little bit on that. And actually, to me, this is one of the least interesting little questionable aspects of the Standard Model. So let me just say something about this now. I started my PhD in 1985, and in the UK, still to this day, all new PhD students in astronomy attend a summer school organized by what is now STFC. In my day, it was SERC, the Science Research Council. And there are lectures on everything to do with astrophysics and cosmology and planetary physics and everything. You know, basically, it's a crash course in astronomy. I really enjoyed that school. And one of the lecturers was Richard Ellis, and he gave a couple of lectures, I believe, on cosmology, observational cosmology. And he, during that, gave us the state of the art for the Hubble constant as of 1985. And you'll see that the Hubble constant, there were two groups, basically. One was high and one was low. De Vaucouleurs went for a high value, and Sandage and Taman, and others, of course, there's not the only ones. But you'll see that if you take the correct value now to be about 70 kilometers per second per megaparsec, of course, then that value is 3 sigma away from the lower one and also 3 sigma away from the higher one. So the moral of this is that astronomers are really not that good at estimating their errors, and that 3 sigma discrepancies do happen. So actually what has happened now, and I think I have this actually very nice review article about challenges for modern cosmology is on the archive. I don't think it's published yet, but I actually posted this on the blog because I think it's quite nice. Here is a whole load of other constraints on the Hubble constant. The Hubble constant, of course, not constant. It's the Hubble parameter is not constant. The current value is the kind of notional expansion rate, if you like, at the current cosmological time. You'll see that things that use the CMB are generally quite low, 67, not as low as 55 though. And things that are stellar indicators are typically higher, and these are the Cepheids, the supernovae and things. And the discrepancy there is something like 3 sigma. So I've been running a poll on the blog about whether people like this think that there's something really fundamental about this. I think the answer is that I don't know, but I'll say something about this. People usually talk about the Hubble discrepancy, the Hubble tension, as a tension between early measurements, CMB, at the last scattering surface, and late measurements, which are basically kind of modern, much better versions of the stellar distance indicators that we had way back in the 80s. Now, there is another difference between these, and that is that these measurements here, the stellar indicators, are basically use luminosity distances. That's actually how the supernova type 1a cosmological constraints come in through luminosity distances, whereas these are based on angular diameters. Now, what would be, if it turns out that there's an inconsistency between cosmological distances measured from angular diameters and cosmological distances measured from luminosity distances, then that would be really interesting. And I'll explain why. This is actually from an undergraduate lecture. If you take the standard cosmology described like with GR and the Robertson-Walker metric, then there's a simple relationship between the angular diameter distance and the luminosity distance for objects at a given coordinate. Oops. Coordinate r as it appeared in the metric, and that's just a ratio of 1 plus z to squared. Now, actually, that is not just a coincidence of the Robertson-Walker metric. This is a really fundamental result. It's actually, in posh words, it's called the Etherington reciprocity theorem, and it actually holds for any space-time. Riemannian space-time, any metric theory, basically. It doesn't require the Robertson-Walker metric, although, of course, if you have an inhomogeneous metric, for example, the luminosity and angular diameter distances along a given line of sight will vary from one line of sight to another, so it becomes a local measurement. But if there is a discrepancy between these two things, it basically means that any metric gravity theory is out the window. Now, I'm not claiming that's the case, because we don't have luminosity distances and angular diameter distances to the same sources, generally speaking. And worse, we generally speaking don't have luminosity distances and angular diameter distances to overlapping populations of sources even. However, if this is the reason for the Hubble discrepancy, it shows that you cannot fix it in any way in GR by just changing the energy momentum tensor, because this has got nothing to do with that. It's just a property of the metric and the space-time itself. Okay, so a lot of people are trying to do this by adding some particular energy form into the energy momentum, late time or early time dark energy and things like that to explain this discrepancy. But the reason might well be a lot more fundamental than that, and that's fascinating. There has been some work on trying to test this directly, and this relationship is consistent with the observations at the moment. But it's potentially this is really fundamental physics that would be probed by this relationship. So generally speaking, on the Hubble constant controversy, I'm kind of, because we've been through it before, you know. There are people who believe strongly that the value is high or the value is low. I think it'll be sorted out. It's probably a systematic of some sort. I don't know. But it's, I think, one of the least interesting little curiosities about modern cosmology, which I'll talk about a few later. As we go on. So the model that we have here, as I've taken a little bit out of an old historical work of art here, which is just this success of the standard cosmology is led to it being called the concordance model, in that it seems to fit everything, more or less. And you'll see here is a cosmologist, and there's some postdocs and people around, and there's a sort of radiant glow of satisfaction about the success of this model. And there's some, kind of press coverage indicated by these trumpets and things. I think that's what they are. But if you actually stand back from that and look at modern cosmology in a proper context, you'll realize that although it's on the surface and superficial level, it's very nice. Going on underneath it, there are lots of things that are questionable and which we don't understand at all. I mean, I don't know what's going on in all of these things. I'm pretty sure these people at the bottom here are graduate students, but apart from that, I'm not sure what's going on. Now, so let me just have a look at this standard cosmology. And I think one of the points I want to get across is that we can't really say that we understand that much about what's going on, because the two main ingredients, the dark energy, which I've touched on, and the dark matter, are both completely unknown. And so I just think of those as placeholders, and they're little boxes which help to make a sort of large scale model, but we really need to look inside the boxes a lot more to see if if what's going on inside the boxes, because we don't know. What is the standard cosmology? Well, it's not just 6 parameters, right? It's a whole load of physics and a whole load of possible ingredients. And the standard cosmology is based on Einstein's general theory of relativity, of course. There's a component of cold dark matter, as we saw. There's a cosmological constant. We use the Robertson-Walker metric. That's assuming a cosmological principle. So in other words, the universe on large scales is homogeneous and isotropic. But we also need a recipe for primordial fluctuations, right? So those are a couple of the parameters to do that. And you have to assume, or the standard model assumes, that those are adiabatic, roughly scale invariant with the power law spectrum, and Gaussian. And if you like, you can say that all of this is kicked off by inflation. Of course, there are other things we know exist, baryons, neutrinos, radiation, and so. But there are things that we don't quite know about this, because baryons, for example, that there are tensions which I won't talk about at all about nuclear synthesis, for example, whether nuclear synthesis results are really consistent. So that was the standard cosmological model. And in this slide, a completely different slide, I'm showing the things that are questionable about it, or should be questioned. And you'll see that every one of them has alternative possibilities. General relativity might not be true. I think most cosmologists would like to assume that it's true. Dark matter might not be cold dark matter, or our inference that there's dark matter might be because we don't understand gravity properly. The cosmological constant, again, is a placeholder there. Is it a cosmological constant, or is it some kind of dynamical dark energy? Is the universe really homogeneous and isotropic on very large scales? The direct evidence for that, as I'll mention in a moment, is not that strong, actually. And the primordial fluctuations we now know more about than we ever have through Planck and so on. Adiabatic, scale invariant, Gaussian actually seems to be pretty good, but there's still possibilities of variant from those. I won't say anything about inflation, I won't think. Now, let me just pick on a couple of these just to say some remarks, just to start off stimulated discussion. A few years ago, for the first time, I actually went, because it was the centenary of the publication of this famous paper with the cosmological constant, I went and found the paper and actually tried to read it. And it is actually quite interesting, because it's not at all like the way it's described when referenced in papers. You see, Einstein's paper on the which introduced the cosmological constant actually starts with a discussion of Poisson's equation, and he goes on to talk about how you could modify Poisson's equation on the right-hand side by adding a constant term essentially to it. This is actually, so we all know when we learn general relativity as an undergraduate that originally the cosmology, so here's, this is a little bit schematic, but it's just Einstein's equation, right? So basically with all the A pi G's and things got rid of, and all the indices thrown away, the left-hand side is about gravity. It's curvature of space-time, basically, but that tells you how gravity works. And then the energy momentum tensor is on the right-hand side. So this is the stuff, and this is matter and how it's moving. So a cosmologist's perspective is basically that the cosmological constant was to add something onto the gravity side. That's what Einstein did. Whereas a physicist, or especially particle physicist's perspective, is to add an unknown thing on the other side. It's a different question mark, otherwise there would have been minus sign. So dark, whatever it is, I think dark energy is actually a pretty terrible name for it. It might be a constant, you can move the cosmological constant quite easily from one side to the other of the Einstein equations and get an effective energy source with a definite equation of state. But it's not really the energy that's important here, because the acceleration of the universe is actually the negative pressure, which is the key thing about dark energy. So it's dark tension or something like that. And it's not really dark either, because it just doesn't interact with photons or anything like that. Same with dark matter. Dark matter is not really dark either. It's just transparent. But it also has to be smoothly distributed throughout space. We don't have any idea of really what dark energy is. So I'm just going to leave it at that. And we don't even know which side of the Einstein equations is the best way to think about it, probably, is another way of looking at it. So let me go. So that was just a comment, historical comment about dark energy, just to emphasize this fact that we may be getting gravity not quite right and getting the matter contents not quite right, are two sides of the same coin, really. And both approaches, investigating both approaches to it is a good thing to do. So here's a Kobe map, which I really like looking at. You notice this is early 90s color scheme. So it looks even different, but it's also very low frequency, low resolution fluctuations. But this basically is uniform. The CMB is uniform on these large scales across the sky to about 1 part in 10 to the -5. And once you've taken the dipole out, I'll mention the dipole later, probably. Now, so the universe is, from where we look, is fairly isotropic. 10 to the -5 fluctuations, quite small. It's actually quite a lot smoother than the surface of a billiard ball. And a lot smoother than the surface of the Earth. Now, again, if you don't mind a trip down memory lane, this was one of the first pictures that I saw of the first kind of redshift surveys that came into wide distribution. This is the famous de Lapperron, Geller, and Hooker CFA slice. And you'll see here the distances, depending on what Hubble constant you like. Nowadays, we would regard these as extremely local, but you can see that you are here and you're looking out in radial velocity space. The universe is quite lumpy on the scales probed by this distribution. And so you can't look at a thing like that and say, oh, we've reached the depth where the universe it's a large enough scale for the universe to be homogeneous in terms of where the galaxy distribution looks like. Now, you can't even really say it looking at something like 20 years ago, the 2DF galaxy redshift survey. I think the Stickman thing kind of fits in here somewhere. It's a much larger thing. There are very large structures in this redshift survey. So it's by no means obvious, just on the face of it, looking at surveys like this, that you've reached a scale where you're starting to see no structures as big as the survey, but just gradually something like revealing the pattern on a carpet, just kind of roughly repeats on a large enough scale. And I think I've got Sloan as well, which shows that there are very large structures in these. So that it's only, I think, relatively recently that we've actually started to be able to show that, as far as the distribution of galaxies is concerned, that we have something that's approaching homogeneity. And I think the issue in many analyses of this is that a lot of statistical methods, for example, the correlation function analysis, which people used for the in the 1980s style, before we moved on to Fourier space and started using power spectra, they kind of assume that you have homogeneity, and the estimated correlation functions are forced to behave in a certain way because you assume that. So it was, I think this is one of the first papers that actually took, this is the one of the infrared surveys, galaxy surveys, the PSCZ survey, where we actually don't assume homogeneity and look at the scaling of the correlation dimension, as it's called, of the survey. And basically correlation dimension of 3 means that it's going to homogeneity. And so this is our log to the base 10 of ours. It's about 100 megaparsecs. We're getting a distinct change in the correlation dimension to something close to 3. This was about 2000 that we did this. And then, of course, now with, I do apologize that there's no attribution on this. I will, before I make the PDF, I'll put the reference on here. But here is one of this Wiggle Z survey, which is going out to much larger redshifts, and we'll be seeing there that about 100 megaparsecs, the correlation dimension is becoming close to 3. You can do these analyses without assuming that a priori. But that's just galaxy counts. Of course, what matters in cosmology is whether the Robertson-Walker metric applies on very large scales. And that's not the same as simply saying that the galaxy distribution is smooth or appears to be smooth. In fact, it's the standard cosmology is a bit strange, because if you have scale invariant fluctuations, the Harrison-Zeldovich spectrum, basically, fluctuations in the metric are 10 to the minus 5 all the way up, essentially. You remember the old story about the old lady who thought the universe was on held up by turtles, and the response from the but what's underneath the turtles? Oh, well, it's turtles all the way down, she said. Well, in cosmology, it's 10 to the minus 5 all the way up. And we actually know that this is true. If you look at the gravitational potential fluctuation for a cluster of galaxies, that's about 10 to the minus 5 of its rest mass. So that's giving you that number. And if you look at the CMB, you see 10 to the minus 5 in delta T over T on large scale. So that's that number as well. So there's never a scale in which the universe will be exactly homogeneous. And this makes it a little bit difficult to interpret the evidence for or against homogeneity. Now, I've forgotten what my next, oops. Now, I'm going to come back later in a moment to the question of that homogeneity. So I'll just mention it now, right? It seems to, it's fitting in my train of thought at the moment, which is that the CMB has a dipole in it. We all know that. It's about 10 to the minus 3 in delta T over T. Now, we think that, or in the standard cosmology, that dipole is caused by a peculiar motion of the galaxy, or corrected to the local group, through a frame in which the CMB has no dipole. So is isotropic. Now, if that's correct, then that motion must be generated by local density in homogeneities. And if you go deep enough out into the galaxy distribution, you should see a dipole in the galaxy distribution that lines up with the CMB dipole, as long as you've corrected for any peculiar motions and bulk flows and things like that. But it doesn't actually line up particularly well. And there are a whole number of papers that came out actually in the 1990s trying to determine omega from the alignment of the CMB with local galaxy dipoles. And they all got a very high value of omega in those when you try to do that. And the reason why they got this wrong is that there's actually a contribution to the dipole from quite a long way out. So my point here is that a relatively small modification in the metric in terms of a gravitational potential fluctuation can have a big effect on bulk flows and things like the CMB dipole convergence, which I think, so the amount of direct evidence that we have for homogeneity of the universe is better than it was, certainly, but it's not overwhelmingly powerful. And I think there are a number of papers coming out questioning that. And I think it's very good that people are looking at this evidence for bulk flows and alignments with quasars and so on. Difficult things to do, but all really fundamental challenges for cosmology. incidentally, I'm not going to go all the way back, but that review article that I had the chart of Hubble values from actually has a good discussion and collection of these kind of anomalies to do with large scale inhomogeneity. It's certainly, we obviously want, as a theorist, you want the universe to be described by Robertson-Walker metric, but these things should all be tested. And I still think there's a little bit of wiggle room. So in right, now, I went off my original planned thread. So, oh yeah, so this is the Planck CMB spectrum again. And this is a slide that I take it from a personal paper from a while ago, basically showing that you get these baryon acoustic oscillations in the power spectrum of galaxies. And of course, since then, we've got a lot more about that. And in fact, one of the slides I showed you before showed you how you can use these baryon acoustic oscillations to determine cosmological parameters. But the fact is that because these wiggles are kind of a relic of these things, because there has to be, for these to be small, the amount of matter that's directly interacting with radiation has to be less. So the dark matter is growing in a way which is not constrained by the physics that produces these oscillations, which I maintain are actually Sakharov oscillations. I'm actually writing a review about Sakharov oscillations at the moment. So, anyway, you have to have baryons, but you have to have dark matter in order for the fluctuations not to be very large. The old baryon-dominated cosmologies had really big fluctuations in the primordial power spectrum. So I'm going to move on now to one of the other questionable aspects that I've mentioned before, into the dark matter, which is that we assume, or many people assume, that it's simple, and Occam's razor is a good thing. And it makes perfect sense to choose the simplest theoretical model to start with, rather than the most complicated one. But if you think about it, that we can't, other than that motivation, it's difficult to maintain an argument why the dark sector should really be all that simple. So cold dark matter basically doesn't do anything but gravitate. Actually, it doesn't interact other than through gravity. It's no thermal velocity, negligible thermal velocity, and so on. But as I mentioned in 2005, there are a number of problems comparing cold dark matter predictions with observations. Some of these are on astrophysical scales, so galaxies don't seem to come out right. Galaxy halos, the question is whether they are very centrally concentrated or whether they have a flattened core. I think I've got a picture. It's a very detailed graphic that I did for that. Then there are questions about whether CDM models predict too many satellite galaxies and whether the morphology of galaxies is right under CDM. There's even some question that satellite galaxy positions are actually satellite galaxies around the Milky Way, or M31 in this case, are actually on planar structures, which is difficult, I think, to explain in terms of a cold dark matter model. This work all has to be done with simulations, of course, so you can't just do a back of the envelope calculate probabilities. No doubt if someone like Carlos Frenk was here, we'd argue that this is no problem, but there seem to me to be genuine issues with cold dark matter on small scales. And if we go back here a little bit, particle physicists like dark matter candidates that are supersymmetric particles, and this is actually quite a while ago that I dragged this down, but it's I don't think things have changed that much. The parameter space for possible supersymmetric theories is being eaten away very, very significantly with time. And there's no evidence for supersymmetry that I'm aware of. People can correct me if I'm wrong. And this is a more recent one showing that basically lots of clever ideas for different ways of detecting supersymmetric particles are all providing upper limits, not providing detections. So it may well be that this paradigm is not right. And some of the alternatives are perhaps, I mean, there are varying levels of physical plausibility, in my opinion, but they're fun. So I think one of the things that theorists like to do is to have fun. Oops. So we've had hot dark matter before. You know, it's basically a light neutrino species. We know there are neutrinos, but they don't contribute that much to the cosmological density. The question about warm dark matter would be kind of intermediate mass particle, and self-interacting dark matter, self-annihilating dark matter. Axions, which when I was a lad, axions were actually quite much more massive than they're being talked about now. They were actually sort of 10 to the minus 6 eV or something like that. Now we're talking about very, very light axions as possible dark matter part. And that idea overlaps with an idea called fuzzy dark matter. And then just to reinforce what I said before, the dark matter, there are people who argue that there's no dark matter because we've got gravity wrong. And if you modify gravity, then you can dispense with all these weird things. I actually really like this fuzzy dark matter idea, as I said, mainly because it's fun. And so the idea is that you have a dark matter particle which is very light, ridiculously light, stupidly light, if you like. And that basically means that its de Broglie wavelength is on the order of the scale of a galaxy. Of course, if you have, just to be totally non-relativistic about it, if you have a particle with that kind of de Broglie wavelength, you have to describe it by a wave function, not by particle code. And so you get something that's a little bit like, warm dark matter, because there's something that the wave mechanics produces something like a quantum pressure, and that causes fuzzy dark matter. Now this model is quite constrained, but it's actually, I've got a student working on this at the moment. It's actually quite, you'll realize that some of the knots and things in CDM disappear when you have wave dark matter here. And it's actually to run codes that don't just do particle-particle interactions, but do the Schrödinger Poisson self-gravitating systems. Actually quite interesting challenge to do that. So I just say that I like that. Now I've gone quite quickly through those. I never intended to do an exhaustive list of all the possible kind of exceptions or variations on the standard model, but I just wanted to raise a few examples that showed that when you look inside the box that says CDM, or you look inside the box that says dark energy, there are lots of different possibilities, and some of them are even viable in terms of cosmological considerations. I'm going to move on now to this last passage of slides, which is more. Now this actually reminds me of. I'll leave this until the end, but it reminds me of one of the talks that I gave in Erice, for reasons that perhaps Norma Sanchez will remember. That basically cosmology has got as far as it has because of an interplay between theoretical ideas and measurements. And what we have is a model of the universe. I distinguish between a theory and a model because a model basically has 3 parameters. It has 6 parameters, which you can't predict a priori. So what we do is basically take a model, calculate, ask ourselves what would the universe look like, or what would some particular survey or some summary statistic look like in this model, calculate that forward, perhaps using simulations or perhaps using an analytic calculation, and then you compare it with observations in somehow. But there has to be a circle here. So you have, if there are free parameters, you have to fix them. And so you need some inverse reasoning here. And I think you tend to, this direction, we compute what's called a likelihood of a given observation, given the model. And then we really have to do a sort of cyclic thing like this. When you go beyond a very simple model, like lambda CDM, even this is generally regarded as the hard bit, the inverse reasoning. And it's massively, in some cases, a massive computational challenge to do this inverse reasoning and use the observations to update the model. But when you do a more complicated model, even the forward calculations are difficult. And that's the case, for example, in fuzzy dark matter and a whole load of other things. Modified gravity theory is actually really quite difficult to predict, to do that forward calculation. So the whole business of cosmology is much more difficult for more complicated models. That's not a controversial statement, but it's just pointing out that when I was starting a PhD, forward calculations like this, take this model, calculate something, you calculated only simple things. And that was not the challenging step. This bit of going around was harder. Now it's hard to do everything. So the conclusion of this little diatribe is that it's actually getting harder to do everything in cosmology. Now, I just wanted to say that actually when we analyze data as part of this cycle, we actually have to make some assumptions. There's a model there, right? So if you think about all the pixels on the CMB sky, all the galaxy redshift positions, every weak lensing signal through a galaxy survey, what we're doing essentially is taking all that information and throwing it into a grinder and coming out with 6 parameters. So it's a massive exercise in data compression. And we have to make assumptions in order to do that. In fact, we have intermediate compression. So you take all the CMB pixels on the sky, compress them into a power spectrum, for example, which goes from millions of pixels to a small number, a few dozen power spectrum band measurements is the way it's usually done. But in order to achieve those compressions, you have to, it's worth looking at what you've done, because you throw away some information. You throw away things which are not informative about the parameters of the model. So another interesting thing about the current phase of cosmology is that we've, generally speaking, up till not that long ago, we could get constraints from individual surveys. Now the emphasis is much more on combining not just different kinds of galaxy surveys, but also different kinds of supernovae measurements and all kinds of different things, throwing them all together. But when it comes to the CMB and from the galaxy clustering, we generally dealt with second order statistics, so power spectra and correlation functions. And that's fine because we are assuming the universe is statistically homogeneous and isotropic, and also the initial fluctuations were Gaussian. So you actually don't throw away very much by doing that. In fact, all you throw away is nothing. You don't throw away any primordial information. You throw away information about non-Gaussianity that's developed as the universe has gone into non-linear evolution, which you could argue you're not interested in. So, so here I just thought I'd show you this. I like to throw this into talks just to show you. This panel on the left is a simulation, not a very good one. It's actually just run on a laptop, of the cosmic web structure in dark matter. It actually hasn't got baryons in it, it's just a dark. So you recognize this kind of chains and filaments of the cosmic web. And when you, if that were a galaxy survey, what we do first of all is work out the power spectrum. Now, what I've done on the right-hand side here with the slightly different blue is I did a Fourier transform of this, kept all the amplitudes of all the Fourier modes the same, but scrambled the phases of each Fourier mode. So basically, I've kept the amplitude of each harmonic component as it is, but basically shifted the phases. Now, the power spectrum doesn't care about the phases of these things. So this survey, or this simulation, has exactly the same power spectrum as the one on the left. Oops. But of course, it looks different. And so the point here is that it basically a lot of the morphological information in this is actually provided by phase correlations, not by or mode correlations, let's put it that way, rather than by characteristic scales in the power spectrum. So you are throwing away quite a lot of stuff when you do a power spectrum. This, of course, is nonlinear. This is kind of Gaussian. This is non-Gaussian because it's nonlinear. This is Gaussian, Gaussianized. Here's a more fun one. I think quite a few of you have seen this before. Here's a possible CMB foreground map. This is actually the height above sea level, or mean Earth radius level. Here's that. Antarctica's rather high up. Who knew? And you see that there's the Himalayas and the Andes and so on. So what I've done here, I've got them in the wrong order. What I've done here is to take the CMB, the W map of version of the CMB map. So I took this map and converted it into spherical harmonic modes with amplitudes and phases. I did the same with the CMB map, converted that into amplitude and phase, and then recombined them with the amplitudes of one with the phases of the different one. And so if you take the W map power spectrum, the amplitudes of the spherical harmonic modes, with the phases of the Earth map, you get a map which has exactly the same power spectrum of W map. But I think if you just blindly did the power spectrum analysis of this, you might miss something, because it wouldn't tell you that there are all these very strongly localized features. These are produced by correlations between the modes, not features in the power spectrum. Now, you probably, you'll notice this power spectrum of the Earth is nothing like the CMB. There's a huge amount of large scale power. But if you do the similar exercise there, you'll see it's like running a stupid low pass filter over the CMB pattern, and you will see that it blows up this region close to the galactic plane. But it produces a very distorted version of the CMB map. So this is Earth's amplitudes with the CMB phases. So that should be a homogeneous map with a very peculiar power spectrum. So the statistics you use depend on what information you're prepared to throw away. I mean, that's the original map. So I'm going to skip that. So you can play these games. On the last legs now, nobody's told me to shut up yet, so I'll carry on for a few more minutes. That's just a general thing. So let's go on to CMB anomalies on the light of this. Now, here's an exhaustive list of possible things that might be wrong. Given that the CMB plays such an important role in cosmology, Planck and WMAP, it's interesting to look at some of the issues that arise with that and that have been worked on. Now, this is an exhaustive list because there are 4 types: type 1, type 2, type 3, and type 4, which is anything else. So there can't be anything that's not included in these. So let me just, and the interesting thing post WMAP is that these really haven't gone away, and they're still rather poorly explained. Now, there's the CMB dipole. Of course, there's a 180-degree variation in the CMB, as I mentioned before. And there is an interesting thing about how the mismatch between the alignment of this and large-scale structure measurements and so on. So this is a live question. I wasn't going to talk about that, and I've talked about it already. So let's just look at the anomalies that they are, some of them. So I'm going to go back to the WMAP thing, just because the graphics are a little bit easier to see. So the CMB power spectrum in WMAP and in Planck has a very low quadrupole, much lower than you'd expect for the best fitting model. Okay, this is the temperature polarization cross spectrum, so we won't talk about that. So this is a bit of an anomaly. There's also a strange alignment, if we just go one by one in spherical harmonic modes, between the quadrupole, which is actually rather planar quadrupole. You'll see these are, it's not aligned with the galactic plane, but it is roughly planar, and the octupole. This again, if you calculate the probability, this looks like a feature. These should be randomly aligned if you have homogeneous and isotropic Gaussian fluctuations on the sky. So those are interesting anomalies. You see also that there's an up down thing at low L in the spectrum. You know, I've got Planck, and that basically is a difference between odd and even modes. And some people think that that indicates there might be parity violation somehow in this distribution. And then there's another one. This is actually a rather old one. I should update this one. But there's a north-south power asymmetry on the CMB. So if you actually, there's a difference in the kind of mean, the variance, if you go the north ecliptic region to the north, compared to the south. Okay, so these are things which, on the face of it, should not happen if the standard cosmology is right. If the standard cosmology is right, then the CMB with primordial Gaussian fluctuations should be a two-dimensional, homogeneous and isotropic Gaussian random field. And these are things, these alignments, all the modes are independent, and those kind of alignments and things shouldn't happen. And then if you go into pixel space, you'll see again the WMAP data here, but this is still here in Planck, that there is a cold spot. It is interesting because it's colder than the coldest cold spot that you expect in most simulations of the CMB sky. I'm coming to the end, so I don't be a little bit autobiographical about this. This is incidentally, I wanted to. Part of the reason for including this was to make a joke, and partly was basically to pay tribute to my late PhD supervisor, John Barrow, who I was working with at the Astronomy Centre a long time for my PhD, essentially, when I did this. John was a remarkable scientist, and as his PhD student, I had some interesting experiences with him. In my first, not this paper, but my first paper, I struggled to write it. It wasn't much of a paper, to be honest, but it got published in the end. John helped me write it because I didn't know how to write papers then. And when we got to the version that was ready for submission, he took his name off the paper. And so it was originally Coles and Barrow. And he took his name off, and I was very upset because I thought he didn't want to be associated with such a load of rubbish. But then shortly after it, I realized that he was actually being incredibly generous. He'd worked a lot on that paper, but he felt that it would be useful for me to have a sole authored paper in the middle of my PhD. He did the same with this one, which is a paper I used using extreme value statistics. You know, what is the hottest hotspot on the microwave sky? But looking back, I realized that I made a big mistake in this because I should have written two papers, one on the hottest hotspot and one on the coldest cold spot. And it would have been easier because with Gaussian statistics, they have the same distribution with a minus sign in them. So this idea of using extrema is actually something which is quite an interesting one. And it's one of the statistical tests, which is goes beyond second order statistics because it's much more sensitive to the tails of a distribution. anyway, that's an aside. And I wanted to pay tribute to John in passing on this, because you know, I wouldn't have had a career without him, and I do miss him a lot. I'm going to end shortly, you'll be relieved to know. But one thing that I should say about interpreting these anomalies is A is for anomaly, M is for model. And it goes back to that overall schema that I had for, you know, how the cycle of statistical cosmology works, which is that an anomaly might be improbable given a current model, given a favored model. So you might find something in the data which is actually difficult to predict, has a low probability given a model. But that's not the same as the probability of the model given the anomaly being necessarily very low, right? Because there are a whole load of other things in the data that are being fitted by the model. And you have to take everything into account when you come up to this posterior probability of the model. So when you look at, oh, this cold spot is a little bit colder than the coldest cold spot I expected, you have to bear in mind that there's a whole number of other degrees of freedom in the data that have fitted quite well, and you're just picking one. So it's actually quite difficult to go from these things, and this goes to a number of fields as well, actually, to go from these observations into a statement that this means the model is ruled out, because it doesn't always do that. In fact, it usually doesn't. Now, on the blog, I had a long-running poll. I might actually put it up again in case anyone fancies voting. And I've done this at conferences as well, when I've done a sort of run through all the possible anomalies and tensions in the current model. And I give three options. A is that lambda CDM fits everything perfectly and there's nothing to worry about with any of them. B is that some of there are interesting indications and they should be followed up, but there's nothing particularly compelling yet. You know, nothing is proven yet. And then C is that there's definitely somewhere among all these anomalies, I haven't talked about all of the anomalies, but among them there's definitely evidence of physics beyond the standard model. And on the blog, it's almost exactly a third in each of these categories. And if we were to poll the audience here, I bet it would probably come out to the same thing. I'm actually in B, I think. Partly because I think some of the alternatives that have been suggested are quite fun. But you can decide whether you're A, B, or C. Or you can decide not to decide. Right. So a few years ago, I gave a talk to the Dark Energy Survey collaboration, which was based on, my title for that was The Maximally Boring Universe. So the point is that lambda CDM, things tend to fit lambda CDM. It's only got a small number of parameters, and they're quite simple ones, and it fits. Does that mean that its cosmologies become boring and all that's going to happen is that we get smaller error bars on 6 parameters? I take a very different view on this, and that is that even within the standard model, there are a lot of questions that haven't been answered, and in fact, quite a lot of them haven't been asked. So the questions we have answered have been actually the easy ones, but we've been left with sort of placeholders, as I've said before. And now that this stuff, which actually is boring, you know, so for example, if we worked out that the universe is flat, we don't have to worry about the universe not being flat anymore. We can tighten up the constraints and start looking harder inside the boxes that I talked about, and we can start to get interesting. And that is the interesting phase now, because we're now being able to start, because we can now do these more complicated forward calculations, we continue to get more and more data. We can ask more detailed questions than this and find out what's really behind the standard cosmology. So I don't think it's the maximally boring universe at all. I think we've just opened up the opportunity to ask it much more to ask the universe much more interesting questions. And that's, I think, my end. So I'm finishing there.
Thanks so much, Peter, for this exciting, very clear, fundamental lecture, inspiring answers, reactions, and discussions. So we open now the session for questions and comments. So participants who would like to address questions, comments, reactions to Peter, please raise your hand so we will proceed to ask the questions or point out the comments. So for those active, you can reactivate the microphone for those who would like to speak and raise the hand, please.
I'm going to stop sharing so I can actually see things. All I've been able to see
is up to you. I can, in any case, I hope you can see too. There were some comments or in the chat, in the discussion, but I will ask participants who would like to point out these questions or discussions, please reactivate your microphone and point out these to Peter.
Oh yes, I'm just looking at the chat now. I didn't see that.
Yes, but yes,
yeah.
there are so.
I have a question. Can I have a simple question?
Yes, please. We can. Please, your microphone is very low. We don't hear you very well.
I will try to speak loud. Good afternoon, Dr. Coles. Just one simple question. Is that right? Are you involved with the Euclid space satellite? Are you involved with this program?
Yes, I am. In fact,
oh, that's good.
Maynooth is the only university in Ireland that is. Yeah.
Okay. One question is from the theory. You're a theorist, physician. I understand. You'll be using the data from this program, which is going to be a major program for Europe and for the research. Basically, my understanding is which kind of physical parameters or data are you using to, I would say in brackets, cross-check your theories and equations, and which kind of parameters program to collect, probably to be put in computers, and because it's a very large data you'll be using. My question is, for your theory, which kind of parameters are interesting?
Yeah, so Euclid will do a number of different kinds of measurements, and so it's not kind of like a CMB. It's sort of a hybrid between a CMB sort of survey and a more traditional astronomical telescope, because it's a survey, but it actually has different roles. So we'll be probing a number of things to do with gravitational lensing, to do with galaxy clustering and evolution. There's things that I didn't have time to talk about. It's not just the nature of galaxy clustering as we see it as a local snapshot, but how that's evolved with time, and that depends on the model in quite a lot of detail. So gravitational lensing provides us with constraints on the cosmological, well, basically the density parameter, but also on the rate of growth. We get constraints from galaxy clustering measurements on different combinations, but it's sensitive to there's not just one parameter that you measure.
You seem to have lost connectivity here.
Well, Nick, we can hear you.
Oh, sorry.
Perhaps you had connectivity you didn't want, I think.
Yeah, I got cut off
So
about.
you expect a lot.
Yeah, so it's Euclid is actually a huge collaboration. There's it goes up all the time. There's like 1,400 people involved, but there's a whole range of different science working groups all doing different things with the data. That people are obviously working on the observational systematics and other things, but they'll also, I should say that Euclid on its own is not the answer. There's combinations of Euclid measurements with measurements from LSST and ground-based spectroscopy and all kinds of other things. So what I said in passing during the talk was that actually the era of kind of single experiment things yielding definitive results is kind of past, and we're kind of going into the massive combination of different data sets now. And Euclid is itself a massive combination of different data sets because it will do different things, you know, lensing and clustering and other things, but also Euclid will work better when it's compared with other data sets as well.
Thank you. Nick Kaiser, did you want to say something about that or another? Because I saw you activated your microphone, so do you want to say something more about that or another question?
I had another question.
So please.
Yeah, so thanks, Peter, for a great talk and really nice to see you again. And I like particularly the photograph of you all looking very young. I would never have recognized you in that picture. And doing what was quite common at that time, which was getting your crystal ball out and making wild predictions for what cosmology was going to look like in the future. And I wanted to, and you sort of came back to that at the end, that sort of style of question. I want to pose it to you in a slightly different way, just sort of thinking about the background, the way I see it in broad terms. There was a highly active phase 10 or 15 years starting in 1915, right? With general relativity, we live in a universe containing galaxies and it's expanding. And within a few years, the discovery of dark matter, right, by Zwicky. And then it goes quiet for 40 years, right? And then there's the CMB, which is now an observational revolution, whereas the other one was maybe largely theoretical. And, Big Bang nucleosynthesis, extending those ideas, you got inflation. And really, that's what we're testing now, right? It's gone quiet again for 40 years. Sometimes when I mention to people in astronomy, we're testing a theory from 1979. They can't believe oops. It's so slow. So what's going to happen next, in your opinion? Is it going to be a theory revolution, or is it going to be an observation, and when?
So let me just disagree a little bit with one of the things that you said, and that is that to a large extent, we're testing Gaussian adiabatic scale invariant fluctuations, which it's true they come from inflation. Many inflationary models do predict those, but of course, they've been around since 1970, long before anyone thought of inflation. So it's not clear to me that we're actually really testing inflation, although lots of people do work on inflation and they kind of believe it. It's a lovely, I mean, I think it's a great idea, inflation, but we're not really definitely testing it, in my view, I don't think. I had a facetious slide about inflation, actually, which I decided not to show, And that was what you get if you look up inflation in the Oxford English Dictionary. And it has things like pumped up language, baseless notions, and lots of other things. Not that I believe that, I just think it's funny that that's the dictionary definition. If you ask me about what the big thing is going to be next, I would say, now I'm not supposed to say this about Euclid, but I think obviously the dark energy, when you propose an enormous mission like Euclid that costs a lot of money and needs lots of things involved in it, you've got to have a big hook to hang the project on in order to get political support for it. And that hook is definitely dark energy, right? It's probing the dark energy and space-time. Now, the hope is that you find through Euclid that the dark energy parameter, the equation of state parameter, is not -1. Because if it's not -1, then it's not a cosmological constant, and there's a whole new game opens. If I had to bet, I'd bet that we can't distinguish anything from W equals -1 in Euclid or anything else. In which case, measuring W equals -1 with greater and greater accuracy doesn't turn me on at all. And it becomes even clearer than it is now that the cosmological constant is fundamentally a theoretical problem. And we need someone to come and tell us what's going on with the cosmology, what its physical origin is. And I think the next revolution will be in cosmology will be some very smart theorist will come up with a convincing explanation of the cosmological constant, where it comes from in microphysics. And that will change our view, not only about cosmology, but about the way gravity works and the way particle physics works. And it could be that there are people working on that kind of area now. So I think it's actually going to be a theoretical question. And we'll go one step further. The whole standard cosmological model is based on a kind of shotgun marriage between general relativity and quantum field theory, right, at the basic level, our best description of matter and our best description of gravity. And we know they don't fit properly. So that all will come from that, I think. And that's where the next step would be. In the meantime, we have to do the police work, measure everything and make sure everything fits. And if it doesn't, that would be really exciting. But if I had to bet money on it, I think that actually we're going to get the next generation of measurements is just going to give us lambda CDM with smaller error bars on it. That seems to be the most probable outcome. But who knows? I don't. So
you think it's going to be theory and not observation? We won't tell the Euclid people, but you didn't say.
Yes, I think it's based on a subjective prior. I think that I just have a feeling that it's based on the observations that we can make in the Euclid range, that we're not going to be able to tell that it's not a lambda.
Yeah.
And that doesn't, I mean, there's
so
a
my prior for when the next revolution will be is influenced a lot by the fact that it was 240 years between Newton and Einstein.
Yeah, well, you may be right there, but I think I'll be retired by then, so probably.
Okay, thank you.
You're welcome, Nick. Good to see you again. I haven't seen you for ages.
Thanks a lot to both of you. So if more questions, comments, or reactions, please, is the moment. So I see a hand. So please, Uri Sipur, please summarize your point, because otherwise we have no time for all. Please summarize your point addressed to Peter.
Hi, Peter.
Hello.
We met long time at the time of that picture that you showed a long time ago. Anyway, I have one simple question. Imagine that you had the whole money and funding that you could request, which observation or experiment do you think will best help us to solve at least some of the puzzles that you explained in your talk?
That's a really good question. I'm not really an experimentalist, so I wouldn't know how much money we could, how much money it would take to answer the questions that I would like to have answered. I think it's quite clear that we need somehow to be able to extend our current cosmological observations out to much higher redshift and look for other, more compelling evidence for deviations from the standard model. So I would probably go for, a ginormous space telescope or a telescope on the moon. That's an interesting thing for, I think. There seems to be, basically, if you'd asked me that question a while ago, there was a lot of talk about, bigger and better CMB missions, all sky things like beyond Planck and so on. I think now the motivation for going into space was really to get the whole sky thing, and that's not really, I don't think we need that as much anymore. So the next generation of CMB instruments, where we're looking at polarization, B-mode polarization, detecting B-mode polarization, that would be a big constraint. I didn't say anything about that in the talk. I didn't mention.
And also deviation in the energy spectrum.
Yes, definitely. Actually, John and just remembering that John Barrow and I wrote a little paper about departures from the Planck curve in the CMB and what you could learn from that in terms of early universe physics. I think that would be good. So there are experiments on the table that can do things like that.
Yeah, I wanted to say that we probably need to solve at least the problem of, try to solve the problem of tension in H0. We need a direct measurement of H0 in a much higher redshift.
Yes, I agree with that. So that's one of the things that I meant when I looked at much more distant sources. And actually, so if we could get stellar distance measurements out to redshifts where we have, where it overlaps with the big redshift surveys for galaxies, then that would achieve, that would eliminate a lot of the uncertainty, I think, in that. But I wouldn't actually know how to design a telescope that was capable of doing that. Of course, the redshift, the high redshift supernova thing requires you to move in into a particular spectral range, which is currently not available for. So this, current constraints on redshift for supernova are still quite low. You don't get much above 1 really at the moment with those.
Okay, thank you.
Thank you. Let's see if there are more questions. Or I have, of course, I have questions and points besides what I promised to some answer to your blog questions. But I leave always the priority to the audience. And Nick, I see again your so. Yes,
he's in a different room now. He gets a second question because he's in a different room.
Different question, different room. So I'm intrigued by what you said about pointing out the Hubble tension is a tension between DL measurements and DA measurements, right? And well, if we could somehow break the DL equals DA divided by 1 plus Z squared, then that would sit on the face of it, that looks like a really good way to go. But do you have an idea for how to do that? Fundamentally, that seems to be saying that the redshift isn't going like 1 over the scale factor. How can that be? I mean,
yeah. So it's, I mean, basically it's you know, as I tried to explain, it's a standard property of you know, all metric theories that actually happens. But so the ways you can get out of it are to have a space-time with, for example, torsion. That gets you out of that. You can also, if you have physics, if Maxwell's equations don't apply, so if you lose photons for some reason.
but I can do that with grey dust.
Well, no, but
yeah,
you can, but obviously that's there are in principle other measurements that you could use to detect the dust, because it should re-radiate and so on. And yeah, it's true. You know, that's like Fred Hoyle and his iron filings a bit. You know, you could make but you know, there are gravity theories that are not based on. I remember having a discussion with George Ellis about this, and he basically had a nice paper quite a long time ago about all the various things that you could do to violate Etherington's reciprocity theorem. And some of them are things like grey dust, but others are sort of Cartan gravity and cosmology with torsion, non-Riemannian spaces of various kinds, and you break these conservation, or breaking Lorentz invariants, you know, Maxwell's equations.
I think you've got to do something like the ladder.
Yeah.
I mean, because it just seems to me that you've really got to break the connection between redshift and the scale of the universe.
Yeah.
And that's very hard. I mean, I know that there's people like Bruce Bassett and George who would do that, but it's hard to say.
I'd like to mention that the Webb telescope will be going up this fall and should be a pretty good advance next generation telescope. Have you thought at all about what cosmological implications might come out of that?
Well, I mean, you're quite right. I mean, I didn't mention that as in the questions about what would I fund, because it's kind of already about to be launched, and it's already been funded with a rather large amount of money so far. But yeah, I mean, it's actually going to push a lot of observations out to higher redshift, of course, because it's actually pushing into the infrared, basically pushing. It's a bigger telescope. It's in space than the bigger telescope than the Hubble Space Telescope. It works at longer wavelength, and it'll be able to push out a lot of information out to large distances. But it's not a dedicated telescope. Okay, so it's more like a traditional space observatory. It will be doing other things like looking for extrasolar planets and things like that as well. The difference between that and something like Euclid, which is dedicated. So Euclid is a dedicated mission. Its goals are to focus on cosmological considerations, but it will generate a huge amount of collateral information as well about galaxy spectra and distributions and stuff like that, colors and evolution of stuff, which is actually really interesting stuff to have. But I think NGST, as it was when I was younger, it used to be called NGST, the James Webb Space Telescope will definitely tell us a lot about high-red galaxy formation and evolution at higher redshift. But it's not going to be a sort of survey telescope, which is kind of what we need to get big sky coverage and large depth things. So I think one of the ways of looking at this is that in extragalactic astronomy, you have sort of two communities. There's one community that's really interested in how galaxies form and evolve. And it's a real pain that we don't know the cosmology exactly, because we can factor that out and then look at how the galaxies are actually evolving. And the others who see galaxies as only interesting insofar as they can tell you about cosmology. And there's a kind of schism between these two groups, and galaxies are kind of messy. I remember, I think I could just see George Smoot's icon down there. I remember talking to him a while ago, and he was very derogatory about the idea of using galaxies to do cosmology. The CMB is much more pristine and hasn't been messed up by so much non-linear evolution. So I think actually, if you think about those two different populations of scientists, I think NGST will probably more favor the galaxy formation and evolution people than directly the cosmologists. But it remains to be seen. We shouldn't forget that these great experiments and observatories often tend to be remembered for things other than what they were designed to do. And there's still a potential for a huge amount of discovery space, so that they actually detect things that nobody thought they would detect and come up with science which nobody thought they would do. And NGST definitely has a huge potential in, sorry, keep saying NGST. James Webb Space Telescope has a huge potential for discovery science, I think.
Thank you. I just kindly remind that for all interested, for those interested in James Webb, we have the lecture by his said creator or PA and John Matter some months ago, and the discussion and presentations are online in the program of the school available. George, do you like to George, of course, George's Fitzgerald is mute. Please, George, you have now reactivate your microphone, please.
All right.
Yes.
Hi,
Thanks.
Peter. Thank you for your talk. and your derogatory reference. If you were remembering it more carefully, I was derogatory about galaxies to point out there's a real difference between galaxies and electrons. Now, electrons and other fundamental particles, you know, they're all identical. You could even quantum interfere them, and there's no such thing as identical galaxies and whatever. Even gravitational lenses are not such good, you know, perfect images of each other. However, you know, you can do some cosmology with them. You just have to realize they're not conserved, and they're not, you know, they're not quanta. they're not standard candles of any form. They're kind of a dust particle tracer kind of thing.
Yeah, I think that's what it's
right.
I just say that one of the things that's happened in cosmology over the last century is that people have cosmologists have grown up and stopped believing in standard candles and things like that, which they did for a large part of the
they haven't quite. Some people do, and so forth. And I will say this about the James Webb and sort of restate what you were saying, is when you were saying things are, you know, it's what things were sold to do in order to get a big expensive project, of which James Webb Space Telescope is an excessive model. It's well more than twice what it was supposed to be, and it's a huge scale. And but you have some big project that captures people's imaginations, including the funders, and allows you to fund it. But you're right, you often are using that tool that you finally get up to make discoveries that were not what it was sold for. And that's happened with accelerators, that's happened with space telescopes and so forth. So I hope that's the case. And I have colleagues and I have actually have a proposal in for James Webb. We're not as optimistic as Floyd. I don't think it's going to get launched till December, but and that's only because they'll do everything to get it within this year, because otherwise it looks really bad on the charts. But I think by December it should be up. But we would like to use it to monitor the caustics of strong gravitational lenses, which allows you to sort of sort dark matter into various things. And I'm a big fan of the fuzzy dark matter or the wave dark matter, and you would see, you know, the caustic be curved, or you would see primordial black holes if they were such things. think they're not so likely. Or you would be able to see the CDM kind of structures being much smoother and much whatever it is. You could start dividing the dark matter into what category it is, so you know which way to go. So I believe that theory is going to be the big break point in terms of this, but I believe that the fact is, if we can keep getting funding, there'll be a lot of new data coming in, and those new data are going to help point us in the right direction. We saw that in general relativity. If you have a long period where there's no data, the field gets sterile. And when observations start coming in, you get breakthroughs in whole new ways. And cosmology is thriving in recent years because new data was coming in at such a high rate.
Yeah, I agree. I think if I'm allowed to just add one other thing, there's Alfred Hitchcock had a very good word for this sort of thing. And that word is a MacGuffin. I don't know if you know what the word is. When Hitchcock was making film thrillers or action movies of various kinds, he said there's got to be a MacGuffin. And a MacGuffin is the thing that everybody is after at the start of the movie. There might be secret plans, or in the Maltese Falcon, it's a little statue. Everyone starts off by chasing it, and that's the motivation for getting everyone going. But very often in a film like North by Northwest or one of these other thrillers, by the time you get to the end, you've forgotten what the MacGuffin was, what they're doing. Their old relationships.
That's all true.
And it goes on. And so quite often you end up with a whole load of exciting stuff going on, and the actual MacGuffin is kind of incidental by the end of the movie. You don't really care anymore. Now, I'm not saying we don't care about these things, but the point about the MacGuffin is that you have to sell these projects because they're so expensive, because they're international collaborations. The MacGuffin has to be something which a politician can understand, a big thing. Whether the scientists see it that. So for the LHC, for example, the MacGuffin was definitely the Higgs, right? The LHC does a lot.
It was, although that's harder to sell the politician. I kept praying that we would discover extra dimensions, because you could sell that to everybody. I mean, there's nobody that doesn't want to know about the extra dimensions.
Yeah. So something that they can understand from science fiction is probably the best kind of MacGuffin. But to go back a little bit to Nick's point, more data, more measurements, more observations is always good, and it's never going to. It may tell you that you're wrong, but it may, as you say, lead you in an interesting direction. There may be clues from individual objects, like strong lensing, for example. Most of the time in cosmology, we're looking to try and get out to large scales where everything's linear and it's closer to the primordial universe. Strong lensing is an example where you don't want to do that. You have to have very nonlinear structures so you can probe the gravitational potential, the lensing potential there. So there are things that could be important clues there, I think. So, that progress is always, more data is progress, always. But in theory, it's less linear, right? So you could go for a long time thinking you know what you're doing and everything fits all right. And then a crucial observation comes along and you go, we've got to try something else now. So theory is often periods of apparent progress, punctuated by kind of retrograde steps where you have to go in a different direction. But there's no question that in the time that I only started in 1985, right? And I was working on predicting patterns in the CMB. There was no data at all in that subject in 1985. And so it was a lot easier to be a theorist, you didn't have any constraints on what you did. Now it's hard because you might come up with an interesting idea for a theoretical model, but it has to pass through so many hoops now because there are so many independent, potentially relevant observations that you have to avoid the constraints.
Right. And there's a lot more bright young competitors.
Yeah, it was a smaller field. Definitely was a smaller field. No observation. I wouldn't like to be, I shouldn't say this, probably. It's much tougher to start out in cosmology now than it was 35 years ago.
Well, my students always say to me, you had it so, you had it so good. It was all this really easy stuff to do.
Yeah.
I said it wasn't so easy then.
Yes, it's right. I mean, it's not, you're not conscious that it was easy when you were doing it, obviously. But if you look back, I mean, a lot of what we did in the 80s, 90s, and early noughties was all linear physics,
Right.
power spectra recalculations, even things like CMB fast, and all those calculations are actually now part of the standard repertoire. When you look back at them, they're basically quite simple.
Right, and that's the thing that's hard for people to realize. If it's not there and you've got to generate it, it's a lot harder than after you've done it.
Yeah.
Once it's done, it's much easier.
Yeah, you could go all the way back to Einstein and say, oh, actually, look at general relativity. There are quite simple ideas behind it. It's no big deal. But, it was a big deal. I mean, Einstein was a genius. And although, I mentioned the 1905 centenary in my preliminary bit of the talk, again, that was the special relativity paper in 1905 was a great paper, but there were probably others who were going to get there to special relativity, Poincaré and so on. But I don't think anyone was in danger of going as far down the path to GR as Einstein was. But we teach it as an undergraduate level now, so everyone thinks, oh, big deal. But be the first to have the imagination to strike out in a different direction from everyone else. That's actually a challenge, a really strong challenge.